All right, welcome all to this seventh lecture of the Continual Learning course offered at the University of Pisa, Continual AI and AI Doctoral Academy. In this lecture, we're gonna finalize our discussion related to the methodologies, particularly looking for hybrid methods that you can use for learning continually over a stream of experiences, and mostly covering, let's say, well-known seminal works in this area. Then the second part of the lecture instead is going to focus on possible applications of continual learning and tools that you can use, you can leverage, apart from Avalanche, for your own experiments, or start thinking about, research and development ideas and practical applications. So the three main sections are going to reflect these concepts, these topics. We're going to start with the hybrid strategies presentation. Then we will quickly move to the possible applications of continual learning that are mostly relevant today, but even in the future. So I also would like to discuss with you what are your ideas, and if you have maybe some particular visions with respect to possible applications in this area. I think that with a positive and creative attitude coming from students, we can maybe have new perspectives on these. And the third part is going to be more about the continual learning tools and with a particular emphasis on tools similar, let's say, open source tools similar to Avalanche, and maybe different vision and implementation efforts, but something that you can really use without paying for particular services or particularly connected to industrial companies and labs. Okay, so let's start with the hybrid strategies section. So as you recall, we discussed about this idea of having a fuzzy categorization for continual learning algorithms. And so this was one possible ways of seeing the different methods proposed so far in continual learning as divided in regularization, replay, and architectural strategies. But I guess you already started thinking about why don't we come up with methods that can leverage these different set of approaches altogether, since they appear to be quite orthogonal in some cases. And in fact, I think you are mostly correct in these ideas, because all of these approaches have advantages and disadvantages, and work best within specific settings, within specific continual learning scenarios, as we mentioned in the benchmarks and scenario section lecture of this course. And so what we can notice is that some approaches are often orthogonal with respect to each other, so that they can be plugged in together, so as we do in Avalanche with this plugin system on the fly to come up with new interesting approaches that may be better in terms of effectiveness, efficiency trade-off. So for example, quite a common, let's say, idea is to plug together an architectural and maybe regularization strategy, or a regularization strategy with replay, for example. And we're going to see a couple of interesting examples of this hybrid, let's say, implementation. So one thing that would motivate us to pursue this idea, instead of finding a specific, maybe strategy that completely, let's say, and focused on one of those categories, would be to see that, acknowledge the fact that biological learning systems seem to apply several approaches together to learn continually. So for example, it is known that the brain uses some form of replay, some form of neurogenesis, structural plasticity, as well as synaptic plasticity, as regulated by different factors within the brain. So that's possible motivation for pursuing hybrid strategies other than the imminent, let's say, practical evidence that would suggest that these strategies are a bit more robust and able to provide better trade-offs in terms of effectiveness and efficiency. And so another interesting say idea that I'd like to point out is that historically developments in methodologies in continual learning have been focusing on, let's say, simpler strategy that would be focusing on specific approaches to continual learning, and that there's a huge space for exploration and further developments of hybrid strategies. So as you can also see from this plot was created a couple of years back, but there's a lot of space of investigation in these different areas at the intersection of the different categories. So one interesting and well-known strategy in continual learning that can be seen as a strategy at the intersection of replay and regularization approaches is called gradient episodic memory, or GEM, and was proposed by Lopez-Paz and Ranzato back in 2017. It is quite of a seminal work in this area, and I think it nicely conveys this idea of a strategy that would allow itself to maintain a set of representative examples of the past as a replay method, but at the same time, these patterns would be used as a form of regularizer for learning about a new data distribution, about new examples that we encounter over time. So in this case, the main idea is that each weight update should be subject also to some inequality constraints to constrain, let's say, the update so that the losses related to previous experiences, previous tasks, never, let's say, increase and eventually can decrease, so that we are essentially saying that we would like to have a solution for learning from new experiences that will be able to not interfere with previously learned knowledge and eventually improve the knowledge and the ability to solve previously encountered tasks. What we define in the past in the lecture about metrics and evaluation as positive backward transfer. So this gradient episodic memory strategy was indeed also very an important development in continual learning, because it's really shed some light about this idea of positive backward transfer. So not only provide the means to reduce forgetting of things we are learning before, but also eventually improving our ability to solve tasks that we have encountered before while learning new things over time. This strategy and this approach is based on, let's say, an inner optimization loop implemented as a quadratic programming implementation with inequality constraints. And I think this can be summarized quite well by the pseudocode that the same paper provides. So here you can see the main train procedure that is supposed to learn a particular mapping function, f of data, starting from a continuum of data. So this is the nomenclature used in the paper. And essentially what they're saying is that you have a stream of data that can be, for example, in our formulation, a stream of experiences. But in this case, they let's say, add an additional constraint, this idea that you can process, let's say, these data related to these experiences only one time in an online fashion, let's say. So that was the main, let's say, idea of the paper, like towards an online continual learning protocol. And so you would get access essentially over time. This is kind of resembling the for loop in Avalanche, right? But you get access to a particular example, X, Y, related to a particular task, T, so that in the end you have a triple, X, Y, T, that you can handle to learn continually over this stream of examples. And then you are allowed to maintain a working memory, let's say an episode, let's say a fixed memory size, even split in this case in tasks. So you have a kind of separate memory for each task, and you're allowed to update this memory over time. And so after you have computed a particular gradient for the loss to minimize on the current training experience, the example we are processing right now. So this case, the loss computed on the output of our parametric function with respect to a particular target y. The normal, for example, percent pre-loss computed on a new example. Then what we would do is also to look for compute the gradient with respect to the same loss function computed with the current mapping function f of theta on the examples related to all the previous tasks that we have stored in our memory. And so we have the best update, the gradient, sorry, for the current loss and the gradient for the previous loss. And so the main idea, as we mentioned before, is to constrain somehow the update coming up with a new gradient that would not allow for an increase in the loss on the previous task. And so this, let's say, gradient projection, something that would allow for learning the new task but without interfering with the previous task, is indeed the main idea of, let's say, these added inequality constraints and this inner optimization loop that will allow for even a positive backward transfer other than reducing forgetting, or actually not allowing for forgetting. And so this is the main loop essentially. Then once we have, let's say, computed this gradient that is optimal somehow for all these tasks and the current one, then we can actually operate the update to the weight, as always, and gradient the sum, and eventually operate an evaluation of this mapping function over time, computing our, if you recall, the results table, this R table over time that we can compute, so that then we can evaluate the different metrics based on this table. And the evaluation procedure, well, it's nothing so fancy, but essentially is just looping over all the possible evaluation examples and computing the average of the accuracy over time. And so here at the bottom of this slide, you can see also the current, let's say, loss. The loss on the memory computed on the memory examples. That is nothing too fancy, just the sum over all the possible examples contained in the memory of every task we encountered before. And then this is essentially the main let's say, update that essentially is following the idea of minimizing, finding the parameters data that minimize the current loss, but subject to these inequality constraints that says that for every task that you encounter before, the loss currently computed should be less or equal to the loss computed in the previous step. So with the previous, let's say, mapping function. So we're saying that we don't want that this update would interfere with the loss, at least that is computed in the previous step. So this, I think, is a quite straightforward application of regularization on top of a memory of examples, and so this is why I think it can be seen as something at the intersection of the two approaches. Then a second and important, very well known and commonly used baseline, I would say nowadays, for continual learning is incremental classifier and representation learning, or better known as ICAR. And so this strategy can be seen as well, I think, as something at the intersection of the replay category and the regularization one. So in this case, we operate by using a form of distillation for the regularization of the feature extractor. So in this case, we imagine to have a model that can be separated into different components. The feature extractor in charge of extracting relevant and general features, and then a classifier on top will be able to classify these embeddings appropriately based on different classes we encounter over time. And so The ICAR strategy assumes to have access indeed of a set of representative examples encountered over time, and to use them also for distillation purposes, so that the feature extractor is updated based on these new examples and knowledge encountered over time, and is able to not overfit on the new examples based on the distillation. Then there is a form of template matching. So this idea of maintaining a set of newest prototype that we can use for classification. So in this case, we use nearest mean classification classifier, and we can see and discuss it next. But essentially, this is based on this idea of maintaining a set of prototypes somehow that would represent the class of our problem. And so in the ICAR, there's also a more sophisticated examples management is based on herding. So with this idea that you want to not only select randomly your examples from the current experience, but you want to select them a bit more carefully so that you maximize the representational power of a particular data distribution. In this case, herding is used to do so. And one main constraint of ICAR is that it's a bit difficult to scale in terms of, for example, the number of classes, and it also has a quite, I would say, inefficient example management that is not working very well with large memory sizes. So, because every time this herding procedure has to be repeated when you add new examples to create a kind of a ranking of the representativeness of the different patterns. So here on the right, you can see the pseudocode for, let's say, the inference part of ICAR, and the pseudocode for the actual incremental training procedure. And then this, of course, is not really completed as there are different sub-methods that are used and described in the paper. So in case you want to learn more about this seminal work, you invited to look at the actual paper published by Rebaffi et al. As well in 2017. But essentially here you can see in the inference this feature extractor that is able to start from the actual input space and produce an embedding of these D dimensions that would compress somehow in embedding the input representative features. And then what we can do for each of the classes before actually looking for the best one that would represent a class for this pattern is to compute the mean of the examples, the exemplars that we have in memory, and so essentially average them at the embedding levels. You can see we're averaging the output essentially of this function T structure, and then once we have this mean of examples, I would nicely represent in an embedded space all our different classes Y. Then what we could do is to just find the nearest one, right? So we classify, let's say, we extract the features related to this example X, and we see how far is it from all the different means of examples. And so we take the argmin to classify these actual X into a particular Y. This is essentially what you would do in ICAR to classify a new example, assuming that you have already a feature extractor in place and a number of prototypes. Then while you're learning incrementally instead, what you need to do is to do a few things, right? So update the representation and then handle this external memory the best way you can. So in terms of updating the representation, you can actually use again the examples that you have stored, right? And you can also so possibly mixing them with the current, let's say, training data, but also using them as a means of distillation. So you're sure that the feature extractor is not changing so much with respect to the previously learned one, and so you can update the actual weights of the feature extractor with this update representation method that would do essentially the steps we have described right now. And then what you need to do is to eventually reduce the number of examples that you store for each class, for each experience you encounter over time, so that you make a bit of space to store new examples that you just collected from the current experience. So there are two different things you need to do. You need to remove the examples that are less interesting with respect to the previous tasks, and then you have to select some interesting examples that are representative for the data distribution you're modeling in the current experience. And so you can do this with this AirOne procedure. More sophisticated ones exist, but this is the one that is chosen for iCarl. And then you have an updated, at the end of this procedure, you have an updated set of examples and exemplars that you can use for the classifying methods we've just described before. So this is pretty much the main idea behind iCarl, and a number of different alternative variations are have been proposed over time, and but this is still one of the main baseline used for continual learning, and because it is quite flexible also in terms of the scenarios in which it can be tested. Another interesting approach that in this case instead would be using some kind of architectural ideas and regularization ones is progress and compress. Progress and compress was proposed in around 2018 by DeepMind again, and Schwartz et al. In particular, as a scalable framework for continual learning based, if you will, on, let's say, progressive neural networks, as we described to be one of the main, let's say, reference strategy for architectural methods, at least very representative, and AWC, elastic weight consolidation, for the regularization of the learning over new data, right? And so in this case, they try to propose an efficient mix of the two, if you will. So the main idea is to have a single method that is based on two columns. If you recall the nomenclature from the progressive neural network method. So instead of adding a new column for each experience, you just have two columns. And one column is reserved for, let's say, the consolidated memory with this kind of a dual memory system approach we have described also with CWR. And this green one, there will be a column just dedicated, very plastic, very, let's say, easy to change and to mold, so that you can quickly learn about a new task without worrying too much about destroying the information of the previous knowledge. And then some kind of a distillation procedure that would allow to, let's say, transfer the knowledge just learned on the let's say, this column into the consolidated one. So yes, the idea is to have these two different columns and to operate a distillation and consolidation procedure that is regularized with the AWC to consolidate this new knowledge into the consolidated column, this blue one. So there is kind of an alternation of the progress phase in which we learn new things in a, let's say, quicker way through this, let's say, forward transfer capability that is given thanks to these lateral connections and progressive neural networks. But we're also able to compress this knowledge in a compressed phase, C, where we distill this knowledge through knowledge distillation, but using elastic weight consolidation to preserve the weights that are more important for the previous data distribution. And so here depicted in this image, you can see how this progressive and compressed architecture is used over time, in this case, for learning about a sequence of free tasks. And what's nice is that in this paper, they also proposed the, let's say, online WC implementation that would allow you to scale on a larger number of tasks without maintaining a different feature metrics and optimal weights for each of the different tasks or experiences that you encountered over time. So that's quite of an improvement, and essentially allows for applying AWC on larger, let's say, number of experiences. That's why they suggested this framework for a more, let's say, scalable approach to continual learning. But yes, I think it is quite a nice example. You can use the different ideas we already discussed in the past, and you know, try to find better compromises in terms of effectiveness and efficiency trade-offs. And as you can see, by using different approaches, this is totally possible without adding so much new ideas to the magic sauce here in continual learning. So that's a nice suggestion that we can do better just by using different approaches, different ideas from different approaches, traditional approaches in continual learning. So I think that another, and I think the last one, of the hybrid strategies that I wanted to discuss with you is AirOne. AirOne was proposed by myself and other colleagues at Unibo, University of Bologna, in the past, and it's something that we've been developing over time in a number of papers from 2018 and till today. And the main idea here of AirOne was to provide a flexible hybrid strategy for continual learning that would leverage, let's say, the best of the architectural and regularization methods. So A and R here stands for architecture and regularization, and was later also expanded to house also some form of replay. So here in the image, you can see the main method as separated into different components, and so let's say standard neural network. In this case, mobile net version 1 was used just because it's a good trade-off in terms of efficiency and effectiveness. Can be split in two different parts, right? So the low-level generic features and class-specific discriminant features, and final part, let's say that is the final linear classifier output layer on top of it. And so in this strategy, in this approach, we used CWR for the, let's say, output layer, maybe seen as an architectural, let's say, the architectural part of layer 1. We used a custom online implementation of synaptic intelligence for regularizing, let's say, the low-level generic features. And we used the concept of latent replay that we explored, we discussed in the previous lectures, so that we could, let's say, find a good compromise here in terms of efficiency and ability to reduce forgetting at the latent in the latent space. So this, I think, is one of the first approaches that would nicely, say, put together different architectural regularization and replay components. And here I just, let's say, recall to you the main, let's say, regularization part as it is implemented in AWC, if you recall, and synaptic intelligence. So just an additional regularization term that would penalize a change in the weights that are important with respect to the previous data distribution, and essentially this omega k weight, weight in a sense, importance weight, would be computed online just based on the specific contribution of that weight with respect to the decrease on the loss over time. And so this can be very efficient. And in fact, I think AirOne is also one of the few strategies that can work on more than 300 experiences, small experiences, and work in a kind of an online fashion, given it's quite efficient in terms of running time and computational overheads, other than memory. And we report the different timing and let's say more efficiency-related metrics also in this rehearsal-free continual learning over small ID batches that we published recently. Okay, so a possible expansion of AirOne would be also to consider, instead of a more, let's say, a simpler latent replay approach, a generative replay one that would, let's say, replace the external memory, as you can see in the image on the right, with a kind of a generative model that is able to generate activation volumes on demand when we need it. And so we played around with this idea in the past, and there is a new upcoming paper. It's called Generative Negative Replay for Continual Learning from GraphTheory. Sorry, there's a mistake there at all. Where essentially we try to come up with the interesting solutions for training a generator incrementally and in the loop online, essentially. So that's quite challenging. But the idea is indeed is here to share some weights with respect to the discriminator model here. So do not have a separate generative model in charge of this, but essentially share at least, let's say, this main part of the classifier to compress, let's say, these activation volumes in red, and then add a few more layers, a few more, let's say, parameters to be able to generate these examples with a separate branch that you can imagine here nearby, this yellow one, to reproduce again back these activation volumes, right? And so this is quite a challenging task. We realized, even though you are trying to model, let's say, these lower dimensional latent activation volumes. So first of all, it turns out that sometimes this volume, depending on the let's say specific layer in which you try to do the replay, may be also very big with respect to the raw input space. So, for example, if you're working with a black and white image that is 28 by 28, this latent activation volume may have more dimensions than the actual input space. That it seems quite, not intuitive, counterintuitive, but it is often the case. And so, well, you need to choose this specific latent layer depending also on its dimensions. But sometimes, especially when you work also with either dimensional images and input data, then these activation volumes may be too big for the current generation capabilities of generative algorithms. So that's quite challenging. So what we discover doing these activities that even though the quality and diversity of these examples is not that great using current, let's say, generative methods, you can use these generated examples as negative examples, so that you don't use to actually update the weights related to these classes, these examples that you have just generated, but you use them to reduce the problem of learning in isolation that it sometimes appears when you want to learn about a particular new class with just a handful of few examples. So yeah, that was just to mention, let's say, an interesting, let's say, venue of research that we're currently investigating, which we try not only to put together different components coming from the architectural regularization replay approaches world, but also trying to work with more advanced, let's say, generative replay strategies that could be plugged into the system and to make this strategy even more flexible with respect to the specific needs of the learning application of or scenario. So to summarize the ideas related to the hybrid strategies and hybrid approaches in continual learning, I think that while it is true that they are more complex and more difficult to parameterize because you have more hyperparameters, as you may imagine, in general, they can provide improved effectiveness efficiency trade-offs. And This is also more evident when we look at, for example, different competitions that have been posed in this area, continual learning, where winning approaches are often hybrid strategies in continual learning. So that's a nice suggestion to pursue, especially for practical applications, strategies that are hybrid in their nature. And why such approaches are not really well investigated as pure, purely categorized strategies in continual learning, I think they offer a nice path for future research explorations. And I think, especially considering, say, newest work in this area, would be nice to see how we can come up with tunable algorithms, and what I say here as self-adjusting hybrid approaches that, based on a specific scenario realization, so an algorithm is able to customize its behaviors and the selection of a particular approach based on a specific scenario would be very interesting to investigate. So these are essentially the ideas that I wanted to discuss with you about the hybrid strategies for continual learning. And I don't know if you have some questions. I think now would be perfect time to ask them here in class or even at home.
Something here. I will. So yeah, there is a question from Bahar. Is there a continual learning model that uses attention mechanisms, like in transformers, to choose examples to add, to use, or remove from the memory replay?
So we have seen the HAT, if you recall, strategy that is using somehow attention, not to choose, specific examples to use in the memory, but for different purposes. But yes, if that was specifically about exemplars management, right? So no, in that case, I cannot remember any specific strategy that was recognized to use this strategy, at least for this purpose. But maybe there is a new thesis from Mattias and Germano coming up on this topic. I don't know if that's relatable.
In general, there is one work about attention within a dataset, but it's not been applied to continual learning yet. So it could be nice, though,
to investigate. Yeah. So that's definitely something interesting. Thanks for the question. But yes, I don't recall any particular method that has been already shown to be effective with these ideas. Then, any more questions? Okay, so if we don't have any more questions, I think what we can do is to look at the implementations of at least the GEM, iCarl, and AirOne in Avalanche, just to get an idea on how these more complex strategies may be implemented and are actually implemented within Avalanche. If we can get them. Okay, so if we look, as always, within the sub-package training and strategies, here you'll find just a few strategies that has been implemented as say specific classes in Avalanche and not implemented as direct plugins that you can, if you recall, use for orthogonally with respect maybe to other strategies. So GEM here is implemented as a plugin, and the other two strategies are implemented as separate, I'd say, methods. Here you can see iCarl and the AirOne. So maybe we can start with GEM. Okay, so GEM here is implemented as this 150 lines of code in Avalanche, and as child class of the strategy plugin as always. So here the gem plugin takes as input just two main parameters. So the number of patterns, or better examples, for each experience, for example, for each task in the memory. And then it has also this, let's say, memory strand parameter that is the gamma parameter in the original paper that, let's say, would somehow, represent the strand, the enforcement, let's say, with respect to this projection in order of the gradient to favor backward transfer. And so I think that in this case, the gem plugin is just implemented two different callbacks: the before training iteration and the after backward. Also the after training experience. Okay, so before the training experience, before the training of each iteration, what we need to do is to compute the gradient constraints on the previous memory samples. If you recall these inequality constraints that we need to put, in our optimization process, what we need to do is to collect a set of gradients with respect to the loss related to previous experiences. So this is exactly what this method is all about. So before actually starting training on the iteration, what we can do is to compute the gradient on the memory. So this memory attribute we have the plugin with X and Y, and after we have computed the forward and the loss on a particular criterion here detailed, then we can just compute the backward to compute these gradients, and then we can just collect them in this G attribute of the plugin. Then the main, let's say, gradient projection algorithm, let's say, part of the method is computed after backward on the current experience, right? On the current training data. And so here, what we do is to essentially, if I recall it well, okay, I use essentially this method that is implemented at the end of the script, this file, that given a particular gradient and considering the gradients we accumulated in the previous method, computes this let's say better gradient that we can use for the update. And so after this step, what it does is to just copy within the actual gradient this better, let's say, gradient, so that once this after backward operation concludes, the base strategy, if you recall in Avalanche, can actually compute the update as always. So we just inject within the base strategy, let's say, a correction on the gradient, so that then the base strategy can update the model's weights accordingly. And then after the training experience, what we have is just an update to the memory based on the current data of the experience, as we would expect. So here, I'm not going to go into the details here, but you can read the specific, let's say, methods, helping methods that are needed in this implementation. The update memory will just replace into the memory the examples randomly selected from the current experience up to that threshold of the patterns per experience that we want to maintain. And then we have this let's say solve let's say this inequality constraint in quadratic programming. This can be implemented. I think in this case with NumPy and these quadprog dependencies we have in Avalanche as for the original code developed for gradient episodic memory and the main implementation of the method just described. Okay, So this is quite nice because we can use this plugin in conjunction with other plugins as we would normally do in Avalanche. Then in terms of the, for example, iCarl strategy, I think we can see this before. I think it is nicely represents, let's say, a more complex and aptly strategy implemented in Avalanche, and showcase how you can actually implement your own strategy just starting from the base strategy, right? So in this case, the iCarl strategy assumes it cannot be used as just a plugin and implemented as just a plugin because it assumes a couple more things like architecture in the model, specific model to be used, for example, with the classifier that is, as we mentioned, nearest class mean classifier, and other, for example, a particular loss and other things that you cannot easily generalize to any strategy, to any model. And in this case, it is a class inheriting from the base strategies that you would expect, and it adds a couple more parameters that can help you directly parameterize the iCarl strategy. So, for example, the criterion here is default to iCarl loss plugin that we're gonna see next, and the model is also defaulted to a model that is here we go, that is defined, as we mentioned, in two parts, two different parts: the feature extractor and the classifier on top of it, based on this nearest mean classifier. So once we have defined the model, and what we can do is to have a private, say, plugin, just to simplify this strategy definition, that would take charge of handling the memory and operate the eventual transformation, and eventually operate the distillation phase and replay phase. So here, what we need to do is to just add in the list of possible plugins the iCarl plugin we have just defined here, and then to call the, let's say, the parent init method of the base strategy to initialize the rest of the parameters accordingly. Then as you can see, all the juice here is based on this iCarl plugin we are going to describe right now, so the iCarl plugin needs to operate the three different things that are important for iCarl. So the handling of the exemplars, and so updating and reducing the memory when needed with AirOne procedure to select exemplars, the distillation and replay part for the update of the representational layers. It's a feature extractor. So after initialization, I'm not going to bother you with what are the main methods implemented as callbacks. Is essentially these four callbacks. So the after train dataset adaptation. So what we do here is to update once the training ended the dataset, the main dataset that we can have within this adapted dataset. Let's say the sum of the memory with the actual dataset used for training. These are the adapted dataset in the base strategy, if you recall, and then have before training experience callback specialized, so that we can just keep track of the previously seen classes. Essentially, this will be useful for later use. And then have a before forward callback specialized to have to compute essentially the embeddings. you know, starting from the feature extractor forward method implemented by the model. And finally, an after-training experience method that would be based on the construction of the example set, eventual reduce, let's say, the removal of exemplars from the set, and the computation of the class means, so that we are ready to have in inference to use these class means with the nearest neighbor classifier. And then here we have these utility functions as implemented to compute the class means, to construct the example set, and also to reduce the example set when new examples are available, and based on the parameters we have defined in the init part of the method. Okay, so then I think that the AirOne is also another alternative example for implementing a method in Avalanche, since in this case it really doesn't use any plugin, and it can be just implemented you know, as just a child class of the base strategy. And in this case, I think is one, if not the most convoluted implementation we have in Avalanche, since we also redefine the training epoch method of the base strategy. So and you know, even the AirOne is indeed using different components from the three different categories and approaches in continual learning. As you can see here, it has quite a lot of different hyperparameters to fine-tune its behavior. So apart from the, let's say, basic optimizer parameters, what we have is 4 different, maybe 5 different hyperparameters to fine-tune the batch renormalization layers that are used by AirOne and are being found to be quite important for learning from small, let's say, from a few data in a long range of different experiences. But unfortunately, these batch renormalization layers need to be fine-tuned quite appropriately. Then we have the random, let's say, the size of the random memory, that in this case is 1,500 examples overall, not for class. And then we have eventually a particular indication to freeze the layers below a particular one. So for AirOne, we mentioned that you can regularize the feature extractor essentially, or the genetic layers with synaptic intelligence, but an alternative that was proposed in the paper was to also freeze the weights below the latent layer. If you're in a situation, for example, starting from a pre-trained model where these layers are indeed very general already and useful for the task at hand. And so here you can specify, of course, also these behavior by indicating the specific layer you want to have as a latent replay essentially layer, assuming also that all the parameters at the below layers would be freezed, and this would count only for the parameters related to convolutional fully connected layers that you may have, and not for the parameters related to the batch renormalization layers, as proposed from the original paper. And then you have eventually, let's say, the computation of the regularizer for, let's say, synaptic intelligence. So in this case, it's called AWC lambda, and is essentially the parameter controlling the strength of the regularization term, if you recall, in the loss defined by AWC. And essentially here, the implementation, what it does is to, since it is very quick, it computes the importance of each weight, nevertheless, and then enforce or not the regularization term with a different strand in case you want it. So if this lambda term is 0, it won't essentially enforce a regularization in the loss. So it multiplies with whatever it is, and it's always 0. But if you change this parameter, the, let's say, importance values are there for you so that you can actually regularize the appropriate layers. Then there are a couple more parameters that would regularize, let's say, control the optimizer, like the mini batch size for training, evaluation, and so on and so forth. But these are essentially the main parameters controlling the AirOne strategy. And so what it does in the initialization part is to essentially instantiate, in this case, let's say a fixed model that is the mobile net version 1 that is already, let's say, better developed in Avalanche so that it can already substitute the original batch normalization layers in batch renormalization layers, and can also be used to extract the latent activation volumes that you may use if you want to do the latent replay approach in AirOne. So this wouldn't normally be possible in a standard, let's say, mobile net implementation in PyTorch that has not, say, it doesn't cannot be, let's say, parameterized with respect to that particular latent layer that you can use to extract latent activation volumes. So here, what this initialization method also does is to replace the batch normalization layers with batch renormalization layers with appropriate additional parameters regulating batch renorm, and then eventually add the Synaptic Intelligence plugin to this strategy if the strength of the lambda is different from 0, well, it's above 0, and use the CWR plugin nevertheless. This is an important part of AirOne. And then essentially instantiate the optimizer and the eventual loss, other than the different parameters that are accessible to this strategy. And then here for AirOne, we need to define the before training experience, the make train data loader, and eventually also the training epoch method itself that is a bit more convoluted, other than the after training experience. So let's see them quickly here. So what we need to do before training on a particular experience is to essentially make sure that if we are in, let's say, the second experience that we encounter, if we indeed want to freeze some layers, we do so. So we can freeze some parameters related to the previous, let's say, to the layers before the freeze below layer indicated in the actual parameterization of AirOne. And then we can adapt, let's say, parameters of batch renormalization layers, and then we'll operate by instantiating the optimizer, and then what we would do here is just update a few more, let's say, attributes that would be useful for CWR. And yes, this is an important part also, is we need to call the let's say, the before training experience method of the base strategy, well, the original callback, so that Also, the Synaptic Intelligence CWR plugins callbacks will be called as well, right? So these are an important part, as I think we mentioned in the past. I mean, also to call the most often call the super method of the strategy, so that the appropriate callbacks of each plugin that can be called as well. Then we need also to specify the make train data loader callbacks, so that in AirOne we can load appropriately the actual data related to the current training data set, that is the current experience, and the latent volumes activations. So this method is essentially all about this. Yeah, I don't bother you with this specific implementation. But what I think it's a bit more interesting is the definition itself of the training epoch that we didn't touch in other implementation of methods, and we often do not override as a plugin in Avalanche. But this is an example on how, if you need to do so, like in AirOne, you can just, first of all, remember to call the specific callbacks that are called in the base strategy of Avalanche. So here you can see a lot of different callbacks that need to be called at the appropriate point in time. And so a suggestion that we make, if you want to directly adjust and modify the base strategy, especially in these fundamental, let's say, callbacks like train epoch, is to start directly from the base strategy and to adjust it based on your needs, but so that you are sure that you're not changing the order of the callbacks, or you're not forgetting those. And so here, why we need to specify the training epoch? Well, because with AirOne, we need to handle these different embeddings that are taken out from the model once we do the forward pass, so that we can plug them in when we need to directly, when we compute the forward pass on the examples related to the current training experience. So this is essentially what we do here. So we take these different latent activation volumes that are part of the mini batch that we want to use from the random memory, in which just activation volumes are stored. And then what we do is to make the forward pass so that we use the specific mobile net implementation model in a way that we can pass the original row input space examples of the current experience, as well as latent volumes that can be combined on the fly by the model, by the forward pass of the model at the appropriate latent layer. So here we pass the original, for example, row images and the latent activation volumes that can be patched together in a mini batch by the forward method of this particular model implementation. And then we can also ask to return eventually the latent activation volumes of the whole mini batch. That's important because we want to take out these latent activation volumes, possibly to reuse them, to store into the memory, and reuse them in the next update phase. So yes, I think that maybe you can look at this implementation maybe more carefully at home, but then just to conclude, the after training example method, you just need to specify how you want to change the currently stored latent activation volumes into the random memory, and how you want to replace them when you need it, when you are reaching the saturation of the fixed memory. And that's it. So even in this case, a more complex strategy, you can get away with just 300 lines of code. So this, I guess, it's a nice strategy you can refer to if you're interested in developing a new strategy that is quite complex and difficult to fit within the different callbacks of Avalanche, so that you need to rewrite a significant amount of them. Okay, so I think that okay, yes, we can take this moment at the end of the first part of the lecture to have a little break, 5 minutes break, and then we start again with the actual second part of the lecture about the applications and the tools. Okay, welcome back to the second part of this lecture. And so, is there any question related to the methods we have discussed before, to the implementation in Avalanche? Anything? No? Okay, then I wanted to introduce you all to, let's say, the different ideas and related to the application of continual learning and deep continual learning methods we have discussed so far. So this would open a completely new topic in this course. I think it's a bit premature in a sense because we are in the early days of continual learning, and as a field it's quite young. But at the same time, I think it is quite useful to start considering, let's say, possible applications of continual learning methods. And that would indeed also guide future research in this area. So maybe I can also ask you if you have some ideas about continual learning applications, maybe because of your own background and experience. I think that would be very nice if you can just forward these thoughts in the chat, and maybe we can discuss them later. So I think that there are several ways of looking at the different applications of continual learning, and you know, this may not be the perfect way to do so, but I thought it would be nice to start thinking about continual learning applications grouped by where the computation may take place. So if we're talking about algorithms running at the edge, if we are discussing about algorithm principally running on the cloud, let's say remote cloud infrastructures, or if we are looking for a strategy that may be let's say flexibly applied in the continuum edge cloud. As you know, there is like a say recent interest in algorithms that can be flexibly applied different levels in these computation infrastructure from the edge to the fog and the cloud, depending on the specific application needs and privacy constraints and distributed computation capabilities and so on and so forth. So if we stick to the edge, well, continual learning may be seen as a way of diluting essentially learning over time. So in these cases, embedded systems, robotics applications and devices, you know, all these particular, let's say, hardware settings are quite constrained in terms of memory and computational resources, and also time to process the imminent, let's say, source of data that you can gather over time. So here you often need a frequent update of your prediction models based on the fast coming data that is maybe high dimensional in its nature and very noisy, and given this particular constrained set of resources that you have. And so continual learning may be seen as a way to improve the privacy of this system, because you never send the private user data from the source devices to remote cloud infrastructure. You can directly learn continually and act as a filter with respect to the stream of data in an efficient way on device. And you're allowed to do this in an efficient way because, as we mentioned multiple times, continual learning algorithm is all about efficiency and scalability, learning from new evidence. And you can improve through continual learning the adaptation capabilities of these systems that nowadays are mostly based on this idea of gathering new data, sending this data to remote cloud infrastructure, retrain a model or update a model in an efficient way on the cloud, and then send the updated model back to the edge devices. So this is quite slow, and it requires an internet connection that is stable enough and should be always on, right, for the different use cases. I'd say it's quite strange, at least to me, that we need, I don't know, our fridge to be connected to the internet to customize the behaviors of itself. That's quite strange, but it's how things are actually implemented nowadays. Like even for I don't know, smart cameras controlling people that are into our homes, and we often are okay with sending this very private stream of data to let's say remote cloud infrastructures. But I guess that would change quite soon in the market, the IT marketplace, and with solutions that can actually work very well at the edge. Then if we're looking and moving, let's say, our attention to the clouds, well, continual learning in this case may be seen as integrated into more complex AutoML or machine learning operations, MLOps systems that, especially for big companies, are quite important and essentially are based on the idea of updating prediction models in an efficient way as new data are available. And these are quite in line with the continual learning vision, right? So in this case, continual learning may help find better trade-offs in terms of scalability, efficiency, and effectiveness instead of retraining whole prediction models from scratch, as today is the standard in this kind of cloud applications and AutoML systems. This would massively reduce the amount of energy consumption, and in the end, the eventual AWS bill that you may pay for updating your prediction models. And of course, improve the efficiency and enhance also the frequency of the update and the adaptation of these prediction models to the new, let's say, users' need. Then, if we're moving our attention to let's say, a more flexible computation that may happen at the edge, at the cloud, intermediate levels, and so we're talking about more pervasive AI systems, then I think that continual learning may provide interesting solutions for more efficient communication, let's say efficient communications or less communications actually, and bandwidth requirements and stable connections as we mentioned before, and provide a more fluid, let's say more direct control, let's say allocation of the resources and the actual, let's say, computation that may happen at different stages and levels in this continuum. Then another line, let's say, possible applications that I see quite pervasive in the next few years is this idea of patching neural models over time thanks to continual learning, and seeing continual learning as a methodology for patching our AI-based and prediction models-based systems. So as you may have noticed, let's say predictive models are now substituting more and more elements or complex IT pipelines that we have. And so while in the past we use patches in a, let's say, agile methodology to improve, let's say, the quality of our software systems, now with predictive models and machine learning models, this is quite ineffective. So we cannot provide fast patches. We cannot say, okay, this is the new requirements, the data they have, just patch your system, your predictive model accordingly. Or we need to retrain the whole system from scratch. That in software, let's say, design would mean to rewrite the whole system from scratch, rewrite the whole software from scratch. So an analogy to that model in deep learning and machine learning would be to use continual learning to patch your neural model and weights and provide a fast update methodology that would enable you to be in line with the new requirements and new expectations from your users and will reflect the new world you're living in. And so these may be related to security patches, as a fairness patches, if you see that your model is quite biased with respect to specific minorities in your users' segments, and provide fast update, fast patches to your system overall. Then another possible, let's say, future application of continual learning may be in line with this idea of let's say a distributed architecture where you have several agents, several hardware devices working in a synergic way to exchange knowledge they are trained on and they've acquired somehow, and how these can be learned, of course, over time, not just within a fixed, let's say, a static setting, which we don't have the notion or knowledge about the non-stationarity of the environment. So there is here an understudied relationship with parallel and federated learning that we will discuss actually in the next lecture about the frontiers, say, of continual learning. So these are kind of, let's say, it's a possible, let's say, set of interesting lines of applications that I think will be relevant in the next few years, but many more are possible, and I'm sure I'm missing, let's say, relevant application landscape that you may instead find quite interesting for continual learning, and invite you to actually reason about all these different possibilities depending on your specific interests, maybe in different areas of computer science and also related scientific disciplines. So here I wanted to show as an example a video showcasing how you can take what we discussed in this course, so these different strategies, for example, so way of evaluating your system, and then you can move towards more practical and impactful applications in the real world. So this is not, I mean, continual learning is mostly something relegated to research, but I think that relevant applications may be developed since today, and this is an example of a more engineered, let's say, algorithm, continual learning algorithm, AirOne, that we had discussed before, directly implemented in Java and C++, in C++, in an Android application. So this was mostly an effort developed, pushed forward by Pellegrini, Lorenzo, and you can read more about, let's say, this implementation in this paper, Continual Learning at the Edge, Real-Time Training on a Smartphone Device, a recent paper that we published, along with different references here, I think are relevant for the deployment of these algorithms to the real edge. So on a smartphone application running on an average mobile phone. So here, we also created a demo, let's say, of this application that will showcase the features of the core app. This is how we call it. And you, by the way, you can download this app on your own device if you have an Android phone, and you can test it out on your system. You should be able to work on a reasonable, let's say, modern device with Android. And you can find the APK you can install. It is safe to install on a Medium blog post that we published on the topic. So here you see how this application is just running a model in inference to detect. Sorry, let's skip again back. Okay, so here you can see how this application is essentially developed to classify correctly an object that is presented in front of the camera. So if the object is presented within a square, then the object may be classified in different 10 categories: adapters, smartphones, not as smart, scissors, light bulbs, and so on and so forth. Okay, these are just a few classes that our model is already able to recognize in the images that we present to the system. And here we just show that, for example, in this case, the algorithm was able, the model was able to recognize light bulbs and all this stuff that were presented to, even though that they were different from the actual light bulbs, for example, on which the model was trained on, as we would expect, in terms of generalization capabilities from a deep neural network, right? So then what's really nice is to see that we can, using AirOne, we are able instead to learn about new objects, instances or classes we have never seen before, right? So what we do in this application is, well, first of all, recognize that if we are presented with this new adapter we never see before, with this different color, this different shape, we're not able to recognize it. So here you can see that we are confounding it with the smartphones, and what we can do is to just collect new examples. In this case, just changing the appearances and essentially improving the diversity of the examples collected, varying the pose, the occlusions, draw ends, the scale, possibly also the background, well, not in this case, but essentially collecting a few hundreds of images from this short exposition of a new, let's say, training session, new experience. Then, well, we were not able, yes, to see it, but the training was completed in a very fast way, in a matter of a few seconds, because essentially we limited our update on the latest layers in our complex network, not training the whole network with a full backward process, but as in AirOne, limiting our updates to the more specific CWR layers and using a bit of latent replay. So, and I don't know why I cannot control probably this video, but essentially what we were able to show is that we can actually, with a few new examples collected over time with this method, without so much of let's say supervised one by one labeling, we are able to still use AirOne directly on the device to update the knowledge of a particular class, or even in this case, you can see create new classes we have never seen before with the same procedure. So how you can skip labeling in this case? Well, first of all, we assume that the object is quite centered, let's say with respect to the square. So these are actually the image, cropped image that we collect. And then another assumption here is that all the images collected are all related to the same object. So we don't need to add labels here because we added just right now a tab on the specific class we want to update, or we add a new label completely. So we know that all the examples in this case collected are related to the stapler, right? So that's easy. And we can just update the model with AirOne with these new, a few hundreds of examples collected from these new training experience. And as you can see, we are not always able to learn to detect that particular stapler, but we're also able to not forget about the past as we would expect. So this was an example that we tried to develop to showcase that with continual learning methods developed today, you can also achieve interesting results on engineering applications, and that can be used for production even, right, for real world applications. And so we also made a step even further in this direction. So we use this, let's say, demo application to actually solve a real world task. So in conjunction with ERA, that is a company here in Italy working on let's say, energy related projects. So we tried to develop a recycling codes recognition app that, based on images collected related to particular objects, may detect and recognize the recycling symbols that appear if you are in Europe, especially, you see that appear in the back of your products. So essentially, based on these symbols, you can easily understand, let's say, understand where to put a product after you use it, in which, let's say, waste bin, depending on specific regulation that you may have on a particular, let's say, region in Italy or in other countries, right? So the idea is, instead of looking for to the shape of the object, that would help us understand where to classify it in terms of bins. The idea that is quite complex in general. The idea here is to just look at the specific codes and provide to the user the specific label, specific bin in which to throw the actual item. And so, so as you may imagine, this is a quite nice, let's say, continual learning problem, because users that are actually using this app are allowed to, take new, let's say, session, video session, just using the app. And so what we would do in this case is not just to ask the user to provide every time, let's say, the label related to that particular symbol, but what we do is to just refine the bounding box detection when we are actually able to detect the code appropriately. So essentially, we limit our update, continual learning update, to the refinement of the bounding box, let's say, segmenting out here in this bottom image, the actual recycling code. And then we have an overall, let's say, refinement of the detection of the internal text and properties of this symbol. That is not just based on convolutional neural networks and deep learning, but also with, let's say, more of a classical approaches to computer vision that would, in the end, segment really well the text related to this symbol. And then based on this, we decide which kind of symbol we're actually talking about. Okay, so this was just an example to see how you can start from the prototype of a continual learning strategy that you can move towards a more engineering solution and then actually use it in the real world. And this is an example of a interesting application of continual learning at the edge, right? So if instead we are looking in general in continual learning for production, well, and this may happen mostly in the cloud, I think there are a number of limits that really constrain the application of continual learning strategies to these contexts. For example, this idea that it's quite difficult to guarantee quality of service and reduce the uncontrolled outcomes if you really allow a continual learning model, a predictive model, to be updated on the fly in the new observations. So, for example, if you have a robot cleaning your home, then you really want to make sure that this robot is not going crazy, doing something very stupid, or you want to be sure that it is reflecting some quality of standard that you had defined, you have promised your users. So that's always posing some questions about the ability to update a model, maybe directly on the edge, but even in the cloud, if you don't have an appropriate, let's say, evaluation protocol in place to make sure that these can be avoided. But it's quite difficult with continual learning. In general, with an agent that is able to update its internal knowledge over time. Another important limitation for the application of nowadays strategies in continual learning is the fact that performance is really the key KPI for many business applications. So if you ask to any business person using AI in their use cases, well, what they say is okay, it's okay to reduce the AWS bill and to reduce compute and memory usage, but overall, what I'm really interested about is to get that additional, accuracy improvement, that the performance increment. That is what impact the user in the end, right? So this ability to really solve a particular task better than the competitors, and also the fact that for many businesses, the amount of data that they collect is still not that high to enforce the usage of a continual learning strategy. So we're talking still about a few gigabytes of data for many businesses, and if you really, maybe talking about bigger companies, that's more likely to be interesting. But in general, this is not a concern because they have also the money to, allow themselves to maximize the performance in favor of maybe efficiency. So overall, I think these are the three main limitations for the application of continual learning in production systems, and Also, this fact that it's quite easy to fake, if you will, the adaptation of a model, even if there's no training involved. So continual learning is the idea of updating the weights of a model, right, of the mapping function over time. But if you want to just simulate adaptation, you can do it also by ifs and whiles. You know, for example, if you talk with Alexa, you have this, you know, possibility to actually interact with the system and make sure that the Alexa is able to personalize the suggestions and the behaviors based on your own instructions, but that's most often not related to the real update of the models. The predictive models are behind the system. So you can, that's also another thing that you know, would pose, let's say, some questions about this idea of updating a model directly on the fly, and go towards this idea of personalized learning. And then it will be very nice to understand, this is a first attempt in this paper, Continual Learning Practice by AIDA and al. To understand how continual learning would fit in a more complex pipeline that is often used in MLOps or in structured production systems, like the image you can see on the right, where there's no just this algorithm to update the model, but there's a whole lot of different actors at play, components that would be, we would need to take into account the learning strategy at play in a production system. Yep.
About the core output.
Yep.
So do you use a hand model to separate the presence of the hand from the images in core? The image only contains the item, is the accuracy still high?
Yeah, so with respect to the hand, I get this question a lot with the Core 50, the benchmark, and the core app. So what happens is that since the hand is probably, if you use the same procedure to collect examples, always present, then the model is able to understand somehow that that's not a discriminative feature to use to classify the objects. But of course, if you use your hand just to collect the examples maybe of the stapler, well, in that case, that may be assumed from the model to be a discriminative feature. So in that case, you need to pay attention only to the fact that the same somehow collection protocol should be used for the model to not overfit, let's say, and to assume, let's say, that that's a relevant discriminative feature. But if you do so, that's no problem. And if you look at the activation maps, the internal activations of a model trained, for example, on Core 50, where the AND is always present, well, in that case, you see that there are no feature maps that would be activated with respect to the feature related to the AND or corresponding to the location of the AND. So that means that the model is actually not learning to represent in a feature extractor, in the feature extraction, the AND at all. Okay, so moving quickly, since we don't have a lot of time, to a couple of interesting use cases in which continual learning is used instead in production, probably. I think that one of the few mentioned in which that actually is clear to happen is the Google Play recommendation system, where in this paper, TensorFlow extended-based production scale machine learning platform paper, it is clearly, let's say, explained that in order to update the recommender system engine for Google Play, a more advanced efficient strategy is employed using the whole data accumulated over time, but employing this worm-init strategy that can be seen as a simple continual learning strategy, where they just update the previously learned model of the previous experience, the previous step, with all the whole, let's say, data accumulated so far. So that's something that may be seen as what we described as a cumulative strategy, but pay attention that for the cumulative strategy, what we do is to start training from scratch every time on the whole accumulated data, and it has been shown to be a bit more performing than starting from the previously learned model instead. Then another interesting use case is the Tesla autopilot that, as you may know, is based only of several cameras that are available in the Tesla cars that collect different perspectives of the scene. And based on these complex AIDA multi-head neural networks, like massive neural network, is able to, let's say, solve a few different predictive tasks with a single model. So that knowledge of a multitask network is present into this system, but there's no clear evidence that any continual learning strategy is used, even though the description that, for example, Andrej Karpathy is the AI director at Tesla, mentioned during his talk at the Spark AI Summit is indeed a continual learning problem. So if you can see, what they do is essentially have a dual system in the car in which one model is used and is the evaluated one for production, and the other model is used for testing the system so that you can update it, you can change it, you can do whatever you want with the model. That wouldn't affect the actual performance of the car, but it's a way to see how different other models, for example, one that can be trained online, would operate in the same context. But what's interesting is that they actually explicitly say that when they encounter a problem in their autopilot system, what they do is to have a focused collection of examples related to the same scenes and problems. For example, they know that during the gallery, in galleries, they have problems with the autopilot. What they do is to, okay, I know that I have this problem, then I collect and label all these different videos collected from the actual cars. And then what I do is to update my complex Hydra model with these new examples. So it's a form of curriculum learning that is naturally embedded into this autopilot let's say, system that is often retrained, I think, from scratch every time. And so in this case, continual learning may provide a very nice way to update this model a bit more efficiently. Then there are a number of startups that being proposed over time and that I think are relevant for continual learning. For example, the Cogitai one that was founded in 2015 and sold in 2007 and 16 to Sony AI. And what's nice is that it is some startup that was founded by Mark Ring, that is actually the main proposer of the term continual learning. And in a recent continual learning workshop presentation, Henry Rips labeled this company as the only continual learning startup on Earth, and because we know that Mark Ring has a very specific idea of continual learning that's quite different from the lifelong learning interpretation. So this startup was based on this idea of providing a continual learning as a service platform that could be used on the edge or on the cloud in a very flexible way. It was called Continua, by the way. If you want to look at it, there's still, I think, the website up, and you can read the documentation of Continua on the main website. Cogitai. Another interesting startup, I think it's Neural, that had several patents on lifelong deep neural network technology, and was mostly focused on lifelong learning as the main, let's say, its main, let's say, technological feature and advancement over competitors. And it's a very well-funded startup. Well, I don't know if it is still a startup, but it was well-funded, more than 25 million in Boston, and it's handled by the CEO Mark Versace, and was a spin-off company, I think, of Boston University from 2013. And now it's focusing on the quality inspections, vision application. I think it's quite reasonable why. So with vision in particular, I think it's continual learning really is particularly interesting because it's a complex predictive task that needs a lot of computational effort, and so it's out of memory. And I think that sense, continual learning may play an important role. Also, given the main focus of continual learning that nowadays was mostly developed within computer vision. And there is also a more recent startup that I wanted to mention as an example, that is instead focusing more on the infrastructures and how you can start thinking of MLOps systems that can work on evolving data streams. And this is quite of an important shift in ML ops and ML infrastructure in general, to work for more into real world settings, real world and real time settings, which you need to operate in training and inference, more and more promptly. And so online learning, continual learning may play an important role here. And this was an OpenAI, let's say, spin-off company. You may want to check it out. Okay, so just to conclude, because we don't have a lot of time, I wanted also to mention a couple of tools that maybe you can look better at home, and are related to Avalanche. Avalanche is the main, let's say, reference tool that we explore in this course as an end-to-end library for continual learning that is powered by a non-profit research organization, ContinualAI, and is starting to create an ecosystem around it to build, for example, reinforcement learning algorithms, or to reproduce results in continual learning, and many other libraries we are building around it. And was also the receiver of the 1DB Best Library Award at CL Vision, and so this is why we are also using it as our main reference tool. And so yes, I also take this opportunity to remember you that as an extra lecture for this course, as I also updated on the website, we will have this Thursday, I think at the same time at the lecture, so from 4 p.m. to 6 p.m. we have this Avalanche Dev Day, where we discuss about the development of Avalanche, relevant issues, and next steps. And we do this every year, so you're all invited to participate. This will take place here at Seminar Yes, as well as remotely. So feel free to join, and it would be nice to discuss with you all about your Avalanche experience, and eventually gather some suggestion of development for the next few years. Okay, yeah, but I wanted to also say that there are a number of interesting projects that have been developed around continual learning that are worth mentioning. For example, Continuum, that is a data loading library, focusing on the data loading part of the continual learning experiments. Is quite similar to the benchmarks module of Avalanche, but it has a slightly simpler API at the cost of less flexibility. But maybe a good choice if you want to focus on a simple, let's say, experiments in continual learning that maybe already developed your own strategy with Python, or not really leveraging Avalanche, so you may want to check that out. And it is also have access to, let's say, a number of already available PyTorch datasets that you can use. So that's nice. Then we have also another, let's say, toolkit that is more intended as a more comprehensive effort like Avalanche, and it's called Sequoia. And it's an important engineering effort with the grand goal of unifying continual learning research in an overall hierarchy that you can see on the right. And so with respect to, it builds, first of all, on top of Continue, Avalanche, Stable Baselines, other projects, but it has quite a different vision and approach with respect to Avalanche philosophy that is more top-down. So while Avalanche provides these building blocks, and you can arrange them as you want without imposing any kind of structure in your experiments and your application of it, Sequoia has more of this top-down hierarchical approach, where you need to define the scenario you're delving with, and develop your algorithms accordingly to fit into this hierarchy. And finally, there's also a nice append, it is called CLGIM, that is also more of an all-in-one library, similar to Avalanche, that offer a nice integration with PyTorch Lightning. We do not currently support in Avalanche, so that's nice. For example, if you want to parallelize things, and that's quite of an important support in PyTorch Lightning for this. So this is something interesting we are considering as well for Avalanche. But as for the moment, so. And that's it. So here I just listed a couple more interesting software tools you may want to check out. And for all of these, I also added the link that you can click on so that you have a more of a clear picture of all these projects. So that's it for the lecture of today. And I'm open now for some of your questions. I don't know if we have some. No? So here is just the heads up with respect to the Avalanche Dev Day that we're going to have the 16th of December, so on Thursday. So here we just list the specifics of it. And so one thing to pay attention is that we are going to use a different link from the current CL course link that you used so far. So you need to click here and to get access to it. But the main program would be essentially based on the Avalanche beta presentation that we coincide with this Avalanche Dev Day. So that's nice. We're going to have a version, finally a version of Avalanche, and possibly a condev pip package that you can install directly with a version documentation as well. And then we're going to have this panel with, let's say, different players operating in CL that have been using maybe Avalanche, and they can provide a bit of a brainstorming session with the current maintainers of Avalanche that can answer even your questions if you may have some, and maybe discuss future developments of the code base that has this aim of becoming a bit of a more shared and collaborative code base that everyone can use. So it's I would like to discuss this openly with everyone, and it would be nice to get your input as well. Okay, so next time, instead, after the Avalanche Day, so no, actually before the Avalanche Day, on Wednesday, we will instead talk about the new frontiers in continual learning, and we're going to hear from Andrea Costo and Antonio Carta about two specific trajectory, let's say, interesting research venues of continual learning in the context of sequence continual learning and distributed continual learning, respectively. So thank you so much for your attention. I'll see you directly on Wednesday.